Hello, everyone. Okay, so welcome to another live stream here. Let me get myself set up here real quick, and we can get started. So the interesting thing about today's stream is we're going to be doing some vector engine stuff again, so like the low-level side. And we want to do that because we have Vecto, which is our vector database, and it happens to be accelerated with vector engines. And it's essentially it should be giving us a good amount of performance. The vector engine kind of is like an ASIC for our vector database. So yeah, I mean, we haven't had any particular like performance problems when using it, but recently we're trying it, or we were trying like PG vector and other things, and it's like, wow, that's really slow. So I thought it would be worth figuring out exactly how much faster is the vector engine compared to the CPU. And the main problem has been like getting a like-to-like performance measurement. So of course we could compare it to other vector databases, but the thing about Vecto is it's doing the vectorization as well as the nearest neighbors lookup. So there hasn't really been anything that we could like really compare it to. So in this stream, what I wanted to do is kind of get around to measuring it, like doing a TopK on the vector engine, compare it to GPU, compare it to CPU, see what it's like, and then from there we can have like a differentiation point. We kind of see what is the performance between these things relative. It might be very big, or it might be super small, who knows. Yeah, so that's what we're going to do today. So we'll be doing some low-level stuff. What I wanted to do is start from here. So this is an interesting TopK benchmark that Paul found. And it's good because it uses like SIMD. And that's pretty cool. It is not exactly a new benchmark, so it was like 5 years ago. So it might not have like AVX 512 support. But for me, I think that's fine for now. We can just like play around with this and see. And once we get that, we can, I was gonna see if maybe I can do some more stuff with the vector engine, like low level, implementing another paper that I saw. But that just depends on if I'm awake enough to do that. So I think we'll just stick it to this TopK one for now. Anyway, I like that it has this GPU implementation as well. I'm gonna have to find a GPU to run this on. Yeah, it creates a random data set, which I like. And then we have tools for parsing args and stuff like that. So let's install this on our vector engine machine. So first I'll try running the CPU and see how that's like. And then once running on the CPU, then maybe I'll build the GPU version. And pre-release, no, I won't switch to pre-release. I'll stick with that one. Yeah, we'll see if we run the GPU version or not, and then run the vector engine version. So yeah, so let's look into how it works. So, oh, it does have AVX 512. That'd be kind of cool. Because the server I have should have AVX 512. CPU info. Let's see which one. I'm using one I don't usually use. But the silver 4214. Let's just double check that one. Pretty sure it has AVX 512. I think it mentions it down here too. But let's just see. Okay, so we have one AVX 512 unit, so it does support AVX 512. Pretty cool. So anyway, so let's look at this README real quick here. And you can see it has like a scalar implementation and then various SIMD multi-threaded multi-query implementations. So that's pretty cool. And we have a make file. So what happens if I just make? Is doing AVX2, which is a good start. And hopefully I sound okay. Please let me know if my sound is good or not working, or if the music is too loud, because like last time it was actually kind of a little too loud, I think. Okay, so we have CPU run. So let's run that and see what we get. Missing file input. Missing file input. But there's no like really instructions on how to do this. How do I do that? So let's go to the data directory. We got some real data. And then okay, so it has some random data sets in there. So let's look at this real quick. TopK pi. I see, and it also has like a Python implementation of the various things. That's pretty cool. So a CPU run data, CPU run data rand data set. Missing file input. Let's see how this actually works. Let's go to CPU, main CPP. Okay, so we need a -F. And we need a D, which I'm not sure about. Actually, there's a little more documentation here. Hmm. Let's see if it says it in the history. So if we go to data, $37 kilobytes. Oh, it's a data generator. That's interesting. So then ran data 3. Same thing. Data ran data set 3. Let's do this second example. Those dimensions look not great. Let's do something like modern. It could be that this code doesn't work really well on large dimensional data. It wasn't really necessary back in the day. N is the number of vectors. 100 vectors is like not a lot. And we want, so this is saying A, so it's like anti-correlated. It's an interesting data set. I thought it would, if it's ran data, I was kind of expecting it would go a little bit faster than this. I do dig this song in the background. This is it's called Night Driving. It's like a good productivity song. So yeah, I have no idea how long it's going to take. Maybe I should not have such high dimensions. Let's do 10. Okay, so that's 100 vectors. So let's do 100 dimensions. Stats to standard error. R creates a create table statement. That's kind of cool. That's kind of surprising how much slower that becomes. 20, 30, 40, 50. It's like taking a while, but like doable. It just gets like slower and slower as you kind of go over the cache, I guess. There's this Higgs. So let me try that Higgs one. That seems kind of cool. Real Higgs. Then let's download. Oh look, notice options show progress. Higgs set. It should be this one. So it has a ton of instances and 21 features. That's pretty small. I was hoping it'd be a little bit bigger. I mean, it's a lot of instances, so kind of makes sense. But 22 is kind of small. Does it show how big it is? Unfortunately not. So no clue. I think this should be, oh, it's 2 gigabytes. 2 gigabytes is a pretty serious amount of data, but it is kind of small in this dimension. Still pretty good. The taxi data set was the NYC trip data. But I don't think it has a lot of columns either. And then this weather data. It's also very small. Would be, I guess the Higgs is the most like ideal that we can do. Right, log sample, zip sample. And cardinality attributes. That's the dimension. So how many, and then dimensions, and distribution. Kind of wondering how fast that one goes. Data, Python rand.py, wants 100, 1024 random things. see, is that what we want? Okay, and how many lines do we have? We have about 100 lines. Okay. So it was different than I was expecting, but it's 100 lines of 1024 vectors, so that's good. Let's do 1,000,000. And then we'll make a 100 by 10 just to try out the CPU run. This will be kind of cool. I wonder what effect the distribution has on things. Okay, so we'll still, that thing's going to be downloading that data for a while. Kind of picking one of the CPU cores. But if I were to do CPU run F data D100 1024, dimensions 1024, and this 100. So excited, loading data from file. Missing N. There we go. And so we have plenty of memory to do this, so I don't expect that we'll have any issues. Yeah, that is slow. And this is the I think that's the generator, the skyline. Oh. See, so there's like a Skybench project here. Let's look at that because it looks like it's going to take a while. So Skybench. There's some data. Well, I guess this isn't a TopK kind of thing. Interesting. The average data set is also should be a good one too for testing things out. Let's look a little bit more into this make file. So skyline is 8 dims, and TopK we have bench. GPU configuration, and then by default we'll do CPU compiler, which is that. Or you can do the GPU. So pretty simple. Should be easy to add a vector engine version of this. Maybe I should be trying it while we wait. $65 gigs. Is that really necessary? We have 100. It's 1024 times 4 bytes. Why do we need that much for loading that file? Bad alloc. That's interesting. Extracting columns. Okay, so that finished. So we now do have a Higgs.csv, which is 7 gigabytes. That is quite nuts. But a pretty good set of numbers there. A good, very real set of numbers from the looks of it. Running this on the Higgs be a bad idea? Probably a bad idea now. Still creating this one, which is going way too long. So let's delete that one. So that's RMD1. This one was 1 megabyte. So let's create a 10 by 100. This will work fine, right? Yeah. Red by 100 is fine. Yeah, let's do 100 by 100 first. So we'll do 100 by 100 Z. The dimension is 100. It is 100. loading the data. I don't know why 10 doesn't work, but 100 by 100 is fine, and shouldn't be too many numbers. Guessing the loading is all done in a single thread. Let's keep an eye on the memory because it's not looking good. That 100 by 100 is 100 kilobytes. I don't know what kind of thing is going on there. I want to check if this is like single threaded. If this is single threaded, it's like might not even be worth running. It's I'm guessing these are all defined in the make file, so probably running each one after another, which would kind of make sense. They are just single threaded. So going with 100 dimensions is probably a bad idea. Yeah, probably not a good idea. Let's do can I do a 10 by 10? What's wrong with 10 by 10? 100 by 10? 100 by 10 is fine. Why is 100 by 10 fine? N is the number of ones, okay, but still. Okay, now this is a tiny bit of data. We have 100 10-dimensional things. So it should be done. Can it possibly be that slow? It's like super slow. Way too slow. Where's my mouse? There it is. I'm taking how much memory? 24, 25. Boggles the mind. It's like nothing. This file is 11 kilobytes. What are you possibly doing? $44 gigabytes, 50 gigabytes. It's a load of crap is what it is. If you can't possibly, what in the world is it doing? I have no idea. Let's see if we can understand from here. We run first bench TA. Bench TA gets the file, loading data from file. And that would be probably in common. I have OpenMP parallel using 16 threads. I understand I have 24 cores and not 32. That really shouldn't matter for this small thing. What in the world? I don't see how this could take time. Starting bench TA, right? Get C data. TA is here. Bad outlook. It's out of memory. Yeah, never mind. This isn't as cool as I thought it was going to be. I think we'll do something else. That's how in the world can you run out of 128 gigs with a 10 kilobyte file? That makes no sense. Using main. It's the debug.sh script. I'm going to start one and real data. Six threads. Let's do that. Debug. A little bit weird. Okay, so that's 8. That ran. And it has no output. Hmm. I'm going to debug the SH again. Or does this have to be true? Do CPU run. Hmm. Find TopK here, but how do you measure it? I'm not sure. Switch to the appropriate branch to run the algorithms. Maybe I haven't done that. It's so weird to rely on branches for stuff. And debug .sh now. Progress. So weird. What changed in the code? TAH. It's really weird to kind of have branches for stuff. What are we doing on memory? We are using all the cores, so that's good. And we're using a file that's now gone. Okay, but it's now benchmarking. Okay, so now we're good. Now we're getting somewhere. Top 16, threshold of 2. Where is it putting that data? In here, but perhaps it's erasing it really quick. I don't see any like D 268 billion 340 2,684,354,000. Wondering how easy it will be to get the results out of this. Hopefully it has some timings for us at the end. To make a VE version of this, I'm going to have to change this device to like 2. Then change this so that we run NCC on there. And add that here. wonder if TT is time taken. And then this would be milliseconds, hopefully. So 36 seconds to init, 25 seconds to run, and then this one is 36 seconds to init, and 116 seconds to run. Hybrid multi-core algorithm for computing Skyline queries. So let's look at this one. Let's look at the simple algorithm. We need to do init and find TopK. This axis is plus equals 6, 2 plus 2 plus 1 plus 2. It's not 6. Thing returns void 2. Everything kind of shows up in the res. Res comes from AA. Yeah, I'm not sure how well this is going to run on a vector engine. Let's look at the README again. So that's a scalar implementation. Then we start doing SIMDs multi-threaded. Column major order, row major order, vectorized threshold algorithm. Let's look at that vectorized threshold algorithm. That sounds like something I might have done. I guess it uses the threshold first to filter. And it's kind of relying on the priority queue to keep the max. Yeah, it's probably something that won't run very well. Vectoring like this. This benchmark sure is taking some time. There's a lot of time in this single thread too. Then this is the benchmark for the LARA algorithm. And we look at the README again. I have no idea what that is. Yeah, weird. I thought with the threshold being higher and higher, this should like get faster. Seems to be like getting slower. Maybe it's because it's also raising. Yeah, top 16 of that by 4, so it's raising the dimension every time. So that's why it's getting slower. That makes sense, I think. It is spending a lot of time in a single core. We'll have to see. I'm not sure if we'll be able to use this. It's not outputting what I was expecting it would output. We'll leave it running for a little bit, see if it finishes. How many of these is it going to do? Starts. Times equals 2, like n here is 5 and 4. That doesn't seem like it's doubling. We're still in one benchmark essentially. So whatever it is, it's inside of CPU run, which means it's doing 1, 2, 3, 4, 5, 8, 2, 3, 4, 5, 6, 7, 8, 9, 10, possibly, or 11, 12, 13. Yeah, this might take a really, really long time. It's weird. I was kind of expecting to go a lot faster than this. I mean, this is like, for sure it is a good amount of lines that we're looking at. Right, like, is that what, 2 billion, or what are we looking at? We are looking at 268 million rows, which is, it's a significant number, right? Still, it's like doing a lot more benchmarking. Yeah, it's like benchmark, set it, find TopK, and then reset the clocks. And then it does it iteration times, and iteration times are what? It's defined to 1. In the code, debug is defining it to 1. It's doing it twice. It's doing it twice. It's just doing it twice. It's like seems super slow. Like I was thinking it was doing it like 10 or 20 times or something like that. It's doing it twice. 200 million rows, each one with 8. And this one, yeah, it's if we make a paper with these numbers, it's like it's not gonna even make any sense. Weird. The interesting thing when it comes to the vector engine is like these small dimensions aren't really that great for it. The number of rows is perfectly fine, right? But the fact that the dimensions are small kind of like limits things a little bit. So when it comes to the vector engine, we're kind of taking advantage of the fact that we have much bigger vectors, like these days with deep learning and stuff like that. But yeah, I think this isn't going to work out. Yeah, I don't think so. This isn't like the reason why I'm doing this is mainly I want to have like a good reference point, like how does Vecto, or like how does our implementation compare to the competition? And yeah, this is not gonna, unless it was doing this like a million times and getting like an average runtime or something like that, taking way too long. It would be a graph that's just like, you know, some small number, and then you can't even see it because it's so small. Makes no sense. Okay, well, instead of that, although this is kind of going to be a much bigger thing, maybe we can look into this, which is an interesting paper. And kind of relevant. So it's a matrix multiplication optimization that I've had an inkling that something like that has been possible. And I've tried to kind of make an algorithm for it, but I haven't been able to think of one. But yeah, these guys have done it, so they're much smarter than me. And it's an approximation of sorts, which is great. But the great thing about this is that it's an approximation that kind of uses table lookups more than calculation. And the great thing about this is the vector engine doesn't have really support for low accuracy numbers like float 16, things like that. Well, it supports them, it just can't do them fast. It's really architected to do 32-bit and 64-bit very fast. So if we can use this to kind of level the playing field a little bit, that might be good. Mainly because the essentially the vector engine has like 6 teraflops, which isn't a lot these days, but it's not too far off. It's I'll probably have to show it again. So if you can do like NVIDIA H100, right? Like that's the latest and greatest, right? Let's look at the NVIDIA H100. So in here, they have a table of lies. These things here, right? So it says, like the H100 might not be a good one because that is pretty crazy. Yeah, but like essentially it's like they always count the tensor core numbers, right? It's all about the tensor core numbers. And the FP32 is the actual 32-bit, right? And then TF32 is not actually 32 bits. It's, you know, it's like a B float 16, but different. And you can kind of see there's a big jump, right? Like 51 teraflops to 700. That's huge, right? And this number has not been growing as fast as these ones have. And while these numbers are very, very big, depending on the size of your model, you're not actually going to be kind of exercising these things, right? Because you'll be dependent on, so it's essentially how much calculation per gigabyte you're doing. And so just because you have really, really big numbers here doesn't necessarily mean you're going to be seeing good performance, because it kind of depends on the bandwidth, right? GPU memory bandwidth, and how computationally intensive that model is, right? And the big models are kind of a little more, the bigger the model is, the more computationally intensive it is, because the bigger set of numbers. But because of the bigger set of numbers, it's also going to be memory bandwidth limited as well. So essentially, you're hitting these limits before you hit these limits, right? And the vector engine has almost 2 terabytes of memory bandwidth, 1.5, 1.2, things like that. So it's very comparable in here, but instead of 51 teraflops, it has, or instead of 67 teraflops, for example, it has 6. So 1/10. So 1/10 the processing power, but very equal in terms of the memory bandwidth, essentially. So that can cause things to be very interesting. And as in, the vector engine might not always be as slow as you might expect, given that it's like 10x slower, right? Because of the memory bandwidth. The balance there is more interesting. But if you do have something, or one way to get around the memory bandwidth is that you can always go lower and lower in the precision, right? So these lower precision numbers work better because essentially you're not getting anywhere near the tops. The tops doesn't matter. What matters is that you're able to read more of the model in because you're saving on bandwidth. And so even though in a lot of models, doing like kind of reconstructing the numbers from their lower precision, things might be a lot more computation. It's still faster because the NEC can often be the memory. So when it comes to the vector engine, since it only has really support for FP32, it kind of loses out quite a bit. And recently, the guys over at NEC have implemented a bfloat 16 algorithm that works really well. The cool thing about bfloat 16 is you can mask it. Essentially, you just mask the lower bits, treat it as FP32, then mask the higher bits and shift it, and then treat it like an FP32. So that's very useful. You don't get more teraflops because you're still doing FP32 calculations, but because you are now sending less data, half the data, you double the bandwidth, right? So that's pretty good. So that brings us to this thing. So what this thing does is essentially, if we can kind of trade precision and memory bandwidth in a different way with this kind of algorithm, it might be pretty good, right? Because the table entries can be like smaller. So you're like leveraging the bandwidth more. And I think this could be kind of an interesting thing to kind of look at. Not sure if I'll be able to do anything here because it's not a trivial algorithm. But anyway, it'll be interesting to look at and see if it's something that could be implemented on the vector engine, because that would be nice. So if we look at this paper, starting at the conclusion, as you might do when you're reading papers, right? So Madness achieves a 10x better speed quality trade-off than existing methods, right? And it's a form of approximate matrix multiplication, but it's pretty good. That's cool. And it's especially good for CPUs because CPUs have a lot less kind of teraflops. Like if you take the latest Threadripper, I think has the same teraflops as a vector engine, or is like around the same, right? And that's 96 cores. So with 96 CPU cores, you can get the same teraflops as a vector engine, but you're still limited on the bandwidth. It's not at the same level. So this would, work for a CPU too. But I wonder if it's possible to do the same thing in a vector engine as well. Yeah. So let's see. I think there was an implementation of this that we can maybe start from. I think we want, what do we look for? It's called Madness, yeah. Okay, so that's Madness Bench, a standalone. Wow, the guy just recently marked it as that, but 8 years ago. That's crazy. Oak Ridge National. Look at the make. This needs Intel, so I don't have that. Not really worth it. I think I was looking at Bolt. Was Bolt in here? Yeah, Bolt is in here. And it's similar. And this repo now also features source code for Madness. So yeah, so let's give this a try. I wanted to play with this, so let's try it and see what happens. Screw this TopK benchmark. Okay, and let's close this project. And then open Bolt. Do I trust them? I guess I should. It's got a nice build.sh, a clean.sh with virtual env. This is great. Okay, I have more cores than that. So let's do that. Start a terminal. I do have virtual env, right? Python 3 version is x86. That may or may not be a problem. Whatever. Let's do run this build.sh. Control M. Let's fix that with this virtual. Yeah, that sucks. Let's do it this way. Python 3. Python 3 nvm. Yeah, I think that will work a little bit better. Docker. What's it using Docker for? Why do you need Docker? It's trying to run things inside of Docker. Yeah, screw that. We don't need that. Or maybe, I mean, maybe we do need that, but still, don't have Docker on this machine. Okay, so we've done a lot of Python pip installing. Then we don't have again 3. I'm not sure if we're going to have an again 3 in the Yum repositories. We do. Interesting. I thought it was, for some reason, I thought it was like way more new than that. This is like old OS. So let's do it the other way. One thing I tried recently was to install the EOS 3 in a virtual machine. Got pretty close, but yeah, it didn't work. And that would make my life much easier. I could work with, different OSs and stuff like that. It'd be really cool if you could use the vector engine inside a virtual machine. Okay, so let's do that again. Let's get rid of this Docker thing. How does this work? You're just building the Docker and then everything else is just happening on here. Okay, no C+14, so for that we will need to SCL enable the toolset. Hopefully that's new enough. Oh yeah, I'm a light theme kind of guy. So Forgotten Eternals mentioned, this is like, so there's a reason why I'm a light theme guy. I'm a light theme guy because the web is all white, and I'm fine for using dark, but I hate switching between the light and dark. So that's why I don't use it. If I have everything white, then everything will be white. I can open up a Word document and it's white, and I open up an Excel spreadsheet, it's also white. So I'm keeping it white. Even my terminal is white. Okay, so now we need to have a different error. I think I need a better SCL. Which do I have? How do I list my dev tool sets? I forgot. I know how to do that. SCL list or something like that. Got it. Okay. Dash it out. 11 is what I have. And that doesn't have C++ 14, so we need a newer one. Okay. So let's check out dev tool sets that we have available. Okay, 9, 7, 11, 10. Darn, 11 is the latest and greatest that I have here. That's unfortunate. That is unfortunate. If I have everything, should just be able to do that. Standard. Let's see. It's 14. That is command line option. G++, standard C. Yeah, that's fine. Bash build.sh. Or is it finding a different error one? Standard C++ 14. Okay, so where is it getting this C++? Which C++? Should be that. Let's make a little test thing. String. Let's just do standard. The H main. The world. Test.cpp. Data app. Okay. That's what I thought. The build sh is using install. So set up pi cpp source path is current directory, and it's not like a single versus double, right? Yeah, it's fine. Oh, it's using Clang. That's why. Oh man, am I gonna have a bad time? I might have a bad time. Okay, anyway, let's try that. Bash build sh. And in here, let's make this. Yeah, something's not working right. Let's export. Okay, so let's make export cxx is equal to that. CC is GCC. Let's build it that way. So weird. What version of Clang do I have here? I don't have Clang. What is going on with... I haven't done a Blaze thing in a long time. Do I have Blaze? I do. I do not. It shouldn't matter. We have CMake. If I just go to the CPP, after build, build, CMake. Cool. We're using DevToolset. Check for working. See it skipped because I have it defined, right? Yes. Cool. And what is this again? Build, yeah, of course. Build. I don't think we have a config, right? Do your thing. Okay, it is doing a thing. What in the world? Why is this like not working in here? Oh, because it's running make. Said it should be running CMake. Build J12. That would work, right? Cool. So that did build. So we know that much works. Now, if we build, okay, fine. It's, you know, how do you, forgot the dot. There we go. Oops. I'm not a fan of this. Well, okay, I am a fan of this. Clicking on the desktop to make your windows go away. Kind of Okay, the thing that is being built is not here. What is it? Okay, CD build bolt. So make that 12. That was literally what I did. Without the GA12. But something else is doing that. Okay, what is the setup.py trying to do? Run command build ext, which is defined ext. Ah, okay, yeah, build ext is built in. And where is that? Define. Do we need the Python? Maybe we don't need the Python. I mean, it would be kind of cool if this was in Python. It'd make life much easier. So I do want it in Python. Swig. Okay, why does Swig not work with the CMake? Let me try asking. Swig. CMake. Python. Doesn't seem to do what I want. I have those defined, right? Yes, I do. Install. I do have Swig. Did I do that? I don't think so. Let's try this. Nope. Okay, let's go to our build. Right, so we did have a thing that built successfully. Right, and I can do bolt. And it runs. So we know that's okay. At least. But what is causing this to fail? This is not working. And that is completely defined in here. Let me look into this. Although it does seem to be like ticking quite along. Single core. But with this, maybe that is perfectly reasonable. Here are compiler flags. Whatever that is. Let's see, set up pi. Swig. Civic. Yeah, this looks useful. It's like just chugging along. That's pretty cool. I have no idea what it's doing, but it's nice that it's working. What does the build ext command do? Setup Python build tools. Okay, build ext does what? Crazy name. Okay, so this looks more or less what I want. Building. Where can I find info about how exactly build ext works? It's a FAR10. That's pretty cool. Extension, then we have the sources. Yep. Okay, let's compile args. CPP. Do I have CPP? defined? No, I don't. So I should use cxx. We shared. Could I build it manually and have it use that instead? That would be a little bit better. So I go to the CPP, go to build bolt, CMake, build. This is configured wrong. Why? Why is that? I'm such a weirdo using VI in an editor. It's just because I'm old. Maybe I need to get rid of this. Then I can do that. It was a good idea. It is using GNU. Why are you using GNU? Right. This is a different shell. You need to do that. We'll remove the C++ build bolt. And then run that. There we go. Okay, now we got a proper build to go. Okay. Sweet. Seems good. Segfaulted, not so great, but whatever. Maybe that's fine. Okay, so for the next maybe hour or so, I think I'm gonna look into this thing. Okay, and after doing that, I can source VM and activate both in here and here. And then in my Python, I can import bolt or not. Let me look at this build.md again, right? You should be able to do that, and then I should be able to do PyTest tests. And module name bolt. Even if I do that, what is this doing again? Install requirements, install third party, use the apply installer. Did it just fail and I didn't notice it? That could be it. Syntax error. It's because swig is like old. Could be that it's old. There's swig 3. So let's try that. Okay. Let's see. If I remove swig, what will happen? Nothing. Great. Install swig 3. And give that build another try. Much better. So Bolt needs a training phase to build a codebook of distances. And it's basically a cache. Yeah, I agree. And I think you're right. It's kind of trading off memory for compute. And since the vector engine has 48 gigs of RAM, then it can hold a good amount of caching, I guess. So cool. So now that I'm able to do that, I should be able to do the tests. And there's a failure. Which is no good. That's no bueno. But possibly I can play with it anyway. Import Bolt. Cool. I haven't used Bolt before, so I'm not sure exactly how you're supposed to use it. I can do Bolt encoder and fit something. And I should be able to do some matrix vector multiplies. Do some k-nearest neighbors. Oh, it makes me wonder. Okay, so Bolt is an algorithm. It says it also features source code for madness. But there's no Python wrapper for it. And it's Mythrol in the source code. It requires 0 multiply adds. And that's kind of unfortunate when it comes to the vector engine, because the vector engine has FMAs, kind of a lot of them. That's interesting. Looking for a research project. Look at our list of ideas. Seems pretty cool. Okay, let me see what I can do here. Okay, so let's take this. Have some timets. Let's make a new file. We got pi, where I put this in there. Let's print out that. Let's run that. Invalid syntax, because we're in Python 3 land. Okay, it's pretty cool. So NumPy versus blast time, bolt time. So instead of 21 milliseconds, taking 2 milliseconds, which is quite good. If I source NEC bin NLC pi 3. No, I don't want to do I want to source opt ACVE NLC 3 bin NLC vars.sh. Okay. Now let me import NLC pi just to check. And let me look at this because it's been a while since I used this. Like the user guide, some usage examples, basic usage, some NumPy stuff. Okay, so I can do essentially that. Should be able to change it to NLC pi, right? Yeah, as array. So if we look at this, we'll do TVE, or maybe NLC pi, time it timer, lambda, and what I want is this. Time at 5, right? But I want to do VEX is equal to NLC pi as array X, NLC pi as array Q. So I think I'll move it into the vector engine. And then in here, if I do VEX, or no, yeah, VEX to Q for Q and VEQ. And then the same thing, .3f and s format T NLC pi times 1000. Okay, and don't have NLC pi. It's weird because I thought it would be part of the Python install, but that's fine. But yeah, I really wish I could run this in a virtual machine, because or just update this machine. Like, this machine's running CentOS 7, and it's getting harder and harder to run things on Python 3.6. So I kind of want to update. And I was hoping to be able to use Proxmox and just kind of like unify my infrastructure on Proxmox, and then just have, you know, like virtual machines doing with like one vector engine to just focus on that one thing. I really wanted to be able to separate them into their own machines, but it doesn't look like that will be possible. I mean, it's not a, I'm still using like the old version, so I have VE 2.0s instead of 3.0s. 3.0s are the ones that actually had support, like the necessary support for virtualization. So it would still be a hack, and totally understand that, but I wanted to like separate them anyway. Okay, so if I run this now, we can see that took a really long time on the vector engine. It's probably not the vector engine's fault. We run this first up here. See if I can get it to not load. Yeah, it's too small, I think. But anyway, it's cool that it's working on the vector engine at least. Can I do enc2 enc.fit VEX? That would be, or enc2.fit. If that, yeah, it can't work that way, but if it did, it would be kind of cool. And in that case, instead of that, it would be enc2.transform Q for Q and Q. Let's see if that blows up. It might. Interesting. It didn't, and it got much faster. No, much faster than it was before, which is interesting. So let's look into how that works. So it is running, so yeah, it is running on the CPU. So just, you know, dealing with that on the vector engine, it's like reading stuff from the vector engine doing some stuff on the CPU, and the encoder, I'm pretty sure, lives in the CPU. So, but it's like getting its information from the vector, and so it's not a good idea as it is implemented right now. But it is kind of interesting. If you were to do the NLC Pi as NP shenanigans here, how bad would that get? Really? Need to see Pi as NP here as well. That's interesting. Look at that time. It went from 2 to 0. Well, 2 to 1. That is interesting. So it supports enough. So we're encoding and fitting. And the fitting is being run on the vector engine, or possibly, who knows? So we got our encoders, our reduction, our pre-process. There's some reshaping and stuff. There's some means and zeros. This is happening on the CPU, and that's kind of happening on the CPU, I guess. What happens if I run the tests in the current state? Still fail. That is interesting. What are we doing on the CPU? Oh, how do I confirm VE usage? That's a good question. And probably something you should be doing. So what you can do is run VE top, which is an opt VE bin top. That's the new one, VE top. And this VE0 is not the best right now. There's some problems with it. It's missing its shroud for reasons that are stupid. So I shouldn't do anything hardcore on it. But if I run this, you should be able to see, well, something happened, but it's kind of too fast. Let's make this be, instead of time at 5, let's make this time at 50. And let's up the queries from 20 to 200. Yeah, let's try that, see how that works. So if you run this, we should see, yeah, now we're kind of like running something on the vector engine. Unfortunately, this percentage CPU doesn't really mean much and stuff like that. But yeah, so for example, let's try, what did I change? I changed this, right? So if we move that to NumPy, and I move this to NumPy, get rid of the NLCPy stuff. Okay, and get rid of this. This and this. With the big size, we have 22 milliseconds, whereas before, 69. Not exactly too great, but regardless, now it's definitely not running on the vector engine. See nothing happening there. And yeah, so we do see a difference when we turn the vector engine. Now, how to kind of see what's happening in the vector engine. There's a weird kind of implementation detail, which makes this be a little less useful than it should be. Essentially, you might have noticed the CPU is always at 100%. It's always going to be at 100% because it's running a kind of busy loop to poll for stuff when you use it in the way that it's being used here. So if you made specifically a normal vector engine program and run it on the vector engine, you can use the percentage CPU here and it'll be accurate. But when you use VE offloading, which is a CUDA style type of thing where you're running a process on the CPU, the host CPU, and it's kind of calling functions onto the vector engine, that's going to be 100% because that VE offloading process is just 100% looping for things to do, and that shows up as 100% CPU. So you can't really see what's going on there. But if you use VE prog inf equals detail when you run things, and you use the VE, it should print out some stuff about the usage. So if we go here, and let's re-enable these things, and .3fms format to NLCPy times 1000. I think something shows up here. Nah, it's not going to show up because it's not like a program. But yeah, you can totally use VE prog inf equals detail to get information about stuff. And these things are actually documented in here. So if you go to SX Aurora Tsubasa NEC or at Sakurada NEJP, there is some things I think the prog inf is detailed in one of these. Yeah, so if you look at getting started with EEO, it's also the ftrace. You can also use ftrace to like look in to see how, how much each function is specifically taking and things of that nature. And yeah, the trace back for both. The EO debug console is also useful. And I think there was the program. If it's not there, then I think it would be in here it is, proginf, right? Proginf ftrace uses guide. Kind of shows you how to do that. It's a very short document. But essentially, when you have something, and you do this, okay, and then if I run Python through, I think it might spit out things now. Yeah, okay, cool. So let's look at that real quick and see what's going on. So here you can see the program information that spits out later. And it shows you the number of vector instructions versus the other instructions. And the important things to look at are the average vector length. This should be 255 or 256, one of the two. The smaller it is from that, the more of the vector engine's processing you're wasting, essentially. The op ratio. So 0.5 means that only 5% of the instructions that the vector engine itself has processed were vector instructions. So when you're using the non-vector instructions, you're just running it on it's still an out-of-order superscalar CPU, but it's running at 1.8 gigahertz. It's not super fast. So you're not really gaining anything from doing it that way. And then cache misses, 20% cache misses, probably not good. FMA count, number of CPU cores used. This is always going to be 8 with the way it's implemented. But anyway, so that's that. Let's go back to Bolt API. Let's do this thing, and I'll see pi as np here. And let me also do that here. Now, if I run this again, like in this state, we see that the average vector length has increased a little bit. The vector op ratio is now 16%, which is a little bit better. The FMA count is actually, significant, right? And you can see the flop counts, right? And flops is 164 real megaflops in the thing, right? So vector time was only 0.8 seconds of the entire time that we were running. But yeah, you can kind of see a good amount of information here. And with that, you can see, oh, well, maybe I should do something to kind of increase the vector usage, right? Vector length doesn't really correspond to the number of queries here. But yeah. Anyway, so this v prompt proginf is very useful for that kind of stuff. This failed. Okay, well that explains it. Okay, so I think that, yeah, so we got 356, 7, and 126. So yeah, kind of okay. The fact that this is kind of fast is very interesting to me right now, but kind of makes me wonder how much more we can do the C stuff. So let's play with the C stuff, I think. The mithril is the new one, right? So this is the madness, literally. So let's look into this a little bit. Haven't read it before, so it's the first time I'm looking at it. Yeah, it's using a lot of intrinsic kind of instructions, so that's all going to have to be very different when using the vector engine. So mithril HPP has mithril encode, this does 32-bit or 16-bit, 8. Then the mithril approximate matrix multiply struct takes some stuff. So that's the random. Then you can call encode on it. You can scan it. We have a dense looped F32 fused. Now, mithril V1, we have a no. So a lot of times I wish people would implement, like have a non AVX version of their code all the time. The reason for that is that not everybody uses Intel, right? Like if you're on a Mac, right? Like a new Mac these days, you might want to use this on an M3. And having the kind of non-AVX version means that it will at least compile. It'll probably run very slow, and you do need to add the intrinsics and stuff to get it to work right. I always wish they had like a simple version so that it's easy to understand what the algorithm actually is, and then figure out how to like expand it to the things, right? Like as a reference, that would be great. And this is all very vectorizable code, with the exception of these things, but okay. Now bolts API should be the same thing, right? Get rid of that for now. We have bolt-in code, which takes some X with rows and columns, centroids, and returns some bytes, right? Then we have induction, bolt lookup table. And here's the fuse multiply add. If you're using the dot product reduction, then you do that. And if it's the L2 distance, you do something else. So the code is pretty nice, I would say. Set 0 load and shift register left immediate, I think. Shuffle the high and lows. Stream. Okay, and then the implementation side, we have a few functions. Recall. Able to pretty interesting. It would be a pain to implement, for sure. So the bolt encoder is that it would be a pain to implement, and it's a pain to implement because it's like riddled with Intelisms, right? This is implemented where? In pure assembly. TopK. So to make a vectorized version of this, probably have to start from scratch. It's like a little too much to implement it. But to implement it, you need to really understand the algorithm. It's here. But I do want to look at bolt. I kind of want to check the two. What does bolt look like? Is it on archive? I just opened the same one. Okay. Bolts. Yeah, so what I tried here with the NLCPy. So NLCPy is a NumPy thing that, like mostly NumPy thing that actually runs everything on the vector engine. It still has the overhead of moving things into the vector engine and stuff like that. So if all you want to do is move one array into the vector engine, then do a few things on it and then read it out of the vector engine, that's usually actually going to be slower than doing it on the CPU, unless the things that you have to do are super complicated, or you load it in once and then do a bunch of calculations on it, right? So in this case, yeah, it's not going to be too fast. Plus, because the fitting, right, the bolt encoder is implemented on a CPU, when you ask NLCPy to give you the values of the thing, it will be extracting that from the vector engine into the CPU. Bolt does its thing, and I'm assuming that if it does call something in the API that uses NLCPy, then that result would then go onto the vector engine, and because of that, calling the transform is a little faster when you not only have NLCPy happening here, but then also in this Bolt API where I've replaced NumPy with NLCPy. So that makes things a little bit faster, but the fitting happens on the CPU. And yeah, an AVX. So then the next question is about, like, is there no translation from AVX to VE? And not really, because AVX is something like this. Let's see if I can find a good documentation for it. But let's look at the instruction set architecture guide, because I think that has the most. I think that will show the most important thing. Essentially, the vector engine has very, very different instructions to AVX, and that's where the difference is. Those instructions are way down here. So loading and saving, those are pretty simple. But let's say if we look at vector subtract single, right? So of course there is a AVX 512 subtract, right? If we look for that, pretty sure it exists somewhere. I'm not sure why this would have to be in Oracle. Okay, it's a Solaris thing. Let me see if I can find an example which would make things super clear. But it's a really good question, right? Like, what is the difference between the vector engine instructions and an AVX 512? But if we look, while that's loading, if we look at the vector engines subtract, right, you can see it has a vector x, vector y, and vector z, right? And the important thing is vector length. So, and it also has like this vector mask stuff going on. So essentially this one instruction represents this kind of code, right? And the important difference is that with AVX, you're doing things 4 times or 8 times or 16 times. I think it's mostly, you can kind of think of you're doing, you load 8 or like 4 32-bit ints into, or no, yeah, if you load 2 32-bit ints into a 64-bit register, I think it has 128-bit registers. So, or yeah, 512, right? So like 512 by 4, 32, so 16, right? So you have like 16 floats, and if you do subtract, you do subtract 16 by 16. But what if you don't have 16, right? The way you would do it in AVX is you fill in, let's say, the first 5, and then you fill the rest with zeros, and then you do that, right? With the vector engine, there's a register called the vector length register. And what you do is you say, I want to subtract vector register 1 from vector register 2 and put the result in vector register 3. And then how many of those you want is something you put into the vector length register. So you would first load 255 or 256 into the vector length register, and then you call subtract, and that would do 256 at once. Or you would load 5 into the vector length register, and then it would do 5 and leave the rest empty, right? So that's kind of like the major difference. You have a kind of one-to-one correspondence between for loops and the vector engine, right? Like if your for loop has an I and that I has a max, then that max goes into the vector length register. And yeah, in the VE, the max vector length is 256 or 255. It says it here. It says it pretty much everywhere. Yeah, the max vector length and the SX Aurora Tsubasa is 256. So previous generations, it was like 64 or something like that, but it's 256. So if you think about 32 times 256, you know, it's like an AVX 8192, kind of, right? Yeah, so when you write regular C, you would write something like this. And you can see like this is specifically dealing with 8. And then you can change a for loop like this with this kind of hard-coded 8 into a single instruction. But with the vector engine, when you're writing vector engine code, you just write the for loop. It gets converted, right? So you don't need to use intrinsics unless you really need to. But essentially, you need to pass not only, you know, your A and B and your reference to C, but also how many things you want, right? And then it becomes like a for loop of, okay, well, that number is greater than 255, do 255, and then at the end, then you do the remainder, right? It's the same instruction. So that's the major difference. Yeah, and so that's it in a nutshell. So is there a bolt paper? publicly accessible bold paper? Yes, okay. Let's look at this as well. Code blocks. Would be nice if I could like implement this in a simple MNIST type of thing, and then give that a shot. Because I know how long MNIST should take to fit for certain specific like architectures, simple ones and specific. Yeah, it looks decent. Do not understand the algorithm too much there. Approximating softmax classifiers. So, nonlinear pre-processing function that reduced the problem to table lookups. So it's like vector quantization used for similarity search. So that makes sense. However, instead of using quantization function, we use one that doesn't require multiply adds. So that might not be good for the vector engine. Reason being that if we look at the Wikichip vector engine page, which I refer to quite often, and hopefully the ads get properly blocked, we can go to the SX Aurora architecture. And if we look at here, you can see that the vector processing unit has the capability to do 3 FMAs. So we have the FMAs, right? Like we got like what 3 times 32, 96 FMAs. So FMAs, not really a problem, but if we're going to be mostly using the ALUs, that's like there's less of those than the FMAs. So not 100% sure this is exactly what we want, but I have the feeling it's in a step in the right direction. And you have Bernard has a good question. So what happens to AVX intrinsics when they run through the LLVM bytecode? Essentially, they're so if you look at this, right, the FMA that we were seeing here. So this is an assembly block, right? So this will get written right into the stream. And the registers here kind of correspond to these, right? So the compiler goes, okay, right now A is in register 17, and then this is in register 6, and that's in register 4, or whatever. And it will generate the right assembly instruction at that point in time. And your intrinsics essentially do the same thing, essentially. So you can kind of always think of them like this, but I'm not sure there's really anything different. I don't really think so. They're just like a way of converting a specific assembly instruction into a function call, but instead of having to think of what register numbers you're using, you're still just using variables, and you leave it up to the compiler to assign them to registers. Okay, so AMM methods work by projecting A and B into lower dimensional spaces and then performing an exact matrix multiply. And this is something that I think should work in general. Like, if it is possible to take a model and quantize it, like quantize each weight into 4 bits, then it should be possible to reduce that, right? And as like keeping it 32 bits, but just reducing the matrix. I'm not sure I can prove that, but I have the feeling that that's the case. So yeah, I kind of feel like that would be something I'd like to see more of. Or sparsifying it. The other thing that the vector engine is kind of good at is that you have a vector mask register. You have a few of them, I think 32 or 64. So if you have like a sparse matrix of stuff, or really a dense one, you can use the vector mask register to kind of remove certain elements from being calculated. So if you wanted to calculate the sum of just the even indexed ones, like 0, 2, 4, 6, then that's easy. You just put that specific pattern into the vector mask register. And then when you run the add or multiply command, you specify which vector mask register to use. And then only the ones that have a 1 in the bit, so it's like a 256-bit number. Only the things with a 1-bit set in that thing get calculated, and then everything else gets removed. And yeah, it won't make your code kind of execute more flops, but it means that you don't have to slow things down, essentially. So the encoding function. So product quantization. Okay, so this is product quantization. I'll look at that later. And this method works for n much greater than md. I guess that makes sense. I have a g and a function. So we have a hash. So here's, to enable the use of SIMD instructions, the tree is limited to 16 leaves, right? So on the vector engine, this would be 256 leaves. So that might be very significant. Then we can look at Appendix B later. Depends on constant number of indices in the input vector. And it should be stored in column major order, which is the ideal. Split indices and thresholds are optimized on the training matrix A using a greedy tree construction algorithm. That's another thing. It might be that it's better to create like doing the hash on the CPU anyway. Because when you have something like this thing, this isn't for trees, right? It's for arrays. So any tree processing will typically happen here, unless you're using, a really good kind of vectorizable tree implementation of some sort. Which do exist, but so the root of the tree is level 0 and contains all the vectors. And then using this notation, it suffices to characterize the learning algorithm. Tree given these buckets will previous level. Find that we select a fixed number of indices to evaluate. Across all buckets. Using an n greater of 4 offer no clear benefit. Okay. Threshold and need that split, then you create a bucket. So we group vectors whose jth entries are above or below the bucket split threshold. So that's the main thing, right? It's like the vectors. Trying to think of what. How was that threshold picked again? I mean, it doesn't matter right now. So let's see. So one hot representations. Then optimize P condition on G and A bar. Well, it's not a bar, but 8-bit aggregation. So instead of using addition instructions, we use averaging instructions, such as that, or non-saturating additions compute. These instructions compute a plus b plus 1 divided by 2, and this means that they lose information about the low bit instead of the high bit. So did we have an average instruction? I don't think so. It's just sum and divide. I don't remember there being an average instruction. Get rid of the guarantees. So besides this main, all the guarantees bolt. Okay. Let's see, not too many head parameters. Encoding sizes. In general, it looks like it's just always better than bolt, and sometimes quite significantly. This pop count method is something I might want to know more about, because Vector Engine has pop count instruction. I think it's POP. I totally do have a pop count instruction. It's might not necessarily be fast though. The interesting thing about that one, I know it's in here somewhere. There's these complex instructions, and from here, you can see there's a port for these complex ones, right? So there is 3 FMAs, 2 ALUs, a load and store port, but one, like there's one for storing stuff and one for complex. So just because you have an instruction to do pop count doesn't mean it's, necessarily fast. But yeah, it's still 32, right? Like, so you have 32 complexes, so it can do it 32 at a time. But the interesting thing about these ones is that it can do more. Right? So that's an interesting thing. Just looks like, yep, pretty much always better. Bolt accuracy kind of goes down quite a bit, but pretty amazing there, actually. Okay, let's look at Appendix B real quick. Okay, quantizing lookup tables. Since the products of 8-bit values require 16-bit, means quantizing those is necessary to enable vectorization. So you instead use the following approach. Here, T is a tensor of lookup tables for all M columns. Okay, 2 entries equals original base operation. Don't understand that very well, but whatever. Let's now go to madness hash. So MO's 16 leaves is so that the resulting codes use 4 bits. Which is kind of interesting. So given that we have 256, that means that the codes would be bigger. So the optimal split threshold algorithm finds the best threshold to split a bucket in a given dimension. And the sum of squared errors can be just added. I don't know. So that's a good question about, like, have they done everything they need for transformers? I'm not sure, but I don't think you need everything. So a transformer is mostly like matrix multiplies and then softmaxes. And I think they have both of those. So as long as you can do those things, then those are the only things you need to optimize. Like the other stuff are like simple and take almost no time compared to the amount of time it takes to do the matrix multiply. So just having the matrix multiply is good enough, I think. There's a parallel. FBG is also a great thing to look into. Okay, so yeah, so that's an interesting thing. This is all single-threaded stuff. So, and it makes sense because, you know, if you have a big matrix, you split it up. So it's better to split it up higher level than lower level, is what they're arguing for. Makes sense. Can see that. And yeah. So I'm not sure. Like, you know, a lot of phones only do have 2 cores or 4 cores, so not a big difference. But they're going to have 8 cores and 16 cores soon, I think. I don't think that you'll ever have like 64 core phones. I don't think that would make a lot of sense. Well, who knows? But yeah, I don't know. I think having threads is good anyway. Because it's like, I think so my feeling about that in particular is that CPUs, and specifically this algorithm, relies a lot on the cache. So just naively assuming that your algorithm is going to be faster when you add more cores is not really a given, because caches can be small, and when you have 8 cores or 16 cores, that can really affect the performance of your algorithm, especially algorithms like this where memory, it's like a trade-off between compute and memory, right? So I have the feeling they might be surprised at that, oh, when you use 10 threads, you don't have 100x speed up, still around 10x speed up, even with more threads. And if you had something like the X3D, right, like those AMD processors that have a ton of cache, then you see something that's like serious speed up, because it just has just that much more cache. It's caching a distance function so that a large CPU has. Yeah, exactly. Like the bigger your like cache is, the better the results are going to be. But the thing is, like, if you have as you have a bigger and bigger like matrix that you're doing the multiply and lookup for, when you have only one core kind of going through it sequentially, the cache is able to keep up with the memory, because it can kind of go, okay, I need to get this, and then after that he's going to go here, and then I need to get that and load it. So it's really, it's easy for a single core to process slow enough that the prefetching can keep up. And then as you go with more and more cores, one thing that happens is now you still have the same amount of cache, right? So if you have 2 cores now, each core has only half of the cache, and the prefetching now has to do 2 times the same amount of work. And because the cache is smaller, it has to evict more than it did before. And so that starts putting pressure on the prefetcher. And yeah, when you have something that's like all cache is going hardcore, then that can be the end of that. But and it's why like the 7800 X3D in particular is a really good CPU for gaming, because it's not just that it has more cache, but because it has more cache, the CPU, like the prefetchers, are able to keep up with the CPUs essentially. So yeah, and especially in games when you're kind of like have different cores and different threads doing different things, it can be really, really beneficial for that. Not sure it's necessarily good for deep learning because there's a lot of computation in there as well. But if you had something like this, maybe X3D would actually be pretty good. It's kind of interesting that PCA here is actually doing better than Bolt in CIFAR 100. Here, Bolt is like way up here, which is interesting. Number of operations. Okay, I see. And then Madness is way down here, still just as good, which is quite amazing. Yeah, so if you could fill that CPU cache with optimized content, yeah, essentially, like when it comes to the CPU, like if you kind of imagine your desk as the CPU, like the core, right? A register is something that you've written down in your notebook as you're about to calculate it, right? And then the L1 cache is your closet, right? So if you need to get something from the L1 cache, you actually have to get up and pick it up from the closet. The L2 cache is a lot farther than that. I would say it's like going next door or something, right? In terms of like the speed of which, you can calculate things on a page, and how fast a CPU these days running at 6 gigahertz can calculate things in the registers, right? And they have a lot of registers these days. So you can imagine if you need to go and get something from the L2 cache, and you essentially have to walk over across the street to pick up something. You're not going to go get one thing, right? You're going to get a bunch of stuff, right? So the way you kind of get caches, right? Like there's a cache line, and then your entire L2 cache kind of comes into your L1 cache just as you're about to access it. And ideally, instead of you stopping and going over, you kind of have a prefetcher, which is able to go, oh, he's almost done with the things in the closet, and he's going this direction. So if I go to the store now and pick up the next group of things, I can have it here before he needs it, right? And the larger your cache is, the better you are doing that. Now, L2 sounds actually really slow because you have to, it takes time to get up and go outside and go across the street to pick up something. And that's kind of, from the CPU's perspective, that's about how long it takes. But going to main memory to get information, that's like going on a 1 hour drive. It's like so much longer, hundreds of cycles, longer than an L2 thing. So yeah, like essentially the more you can have everything that you need in the CPU cache, the way faster. Like so much of CPUs these days is not limited by the compute, it's limited by the size of the cache. So X3D and that technology, it's not like a panacea, right? It's not solving everything, but it just kind of makes it much easier to get the most out of the silicon. And yeah, something like Bolt is essentially it's a trade-off, compute versus memory. So yeah, having more cache, if you have something like the X3D, which is 96 megs of cache, right? And your data set is less than 96 megabytes. 96 megabytes, it's a lot of data, right? Then that thing's going to be super fast. What is the L2 cache bandwidth in, I don't know, in the 7800 X3D? Yeah, the L3 cache is 96 megabytes. Still, it's L3, so it's going to be a little bit slower than what you want. But you have 8 cores with 96 megabytes of stuff really close. And yeah, I'm not sure what the bandwidth of the cache is, but RAM's speed is slow as hell. That's the main thing. Like 12 cycles. Does it have any? I'm not sure. I'm not sure they have any like bandwidth things, but if we do DDR5, right? DDR5 bandwidth. I need to keep an eye on my battery. It's not. 64 gigabytes a second of bandwidth per DIMM, right? So if you have, something like a 4-channel memory, you have like, it's like 200 gigabytes or 356 gigabytes per second. The vector engine has 1.5 terabytes per second of bandwidth, and the cache will usually operate at like 3 terabytes per second. Now I'm not sure what Intel CPUs can do in terms of cache, but essentially this kind of cache to this kind of bandwidth, I'm expecting in Intel CPUs is closer to this number than to 250, like 64 gigabytes per second, which is because they don't have HBM2, so this is way slower in an Intel machine. Interestingly, in Apple's machines, they're not using HBM2, but you get 800 gigabytes per second with the latest thing. That's pretty good, right? Like that's kind of close to here. So you don't need so much cache in an M3, although it'd probably be better with it. But yeah, DDR is kind of slow. I think DDR5 is still kind of slow when compared to that stuff. Yeah, and it's, the CPU cache should, when you have like a 7 billion parameter model, that's not going to fit in your CPU cache. Unless you have a really crazy, like, I think the latest Xeons from Intel, the ones with like 64 gigs of cache. Cache, they also have HBM2. So, but you can set it up to use so that it uses it as a cache. That will fit and that will work pretty well. But in general, like doing the matrix multiply is it's a predictable thing. You do this part, then you do that, then you do that part. So you can just stream it in as you're about to use it, and as long as your processor can predict that, and you have a nice access pattern for the thing to predict it, then it won't matter that your cache is small, because you're not gonna always use the same thing all the time, right? Like you use it, and then once it's done, you go to the next one, and then when you're using the next part, it knows that, okay, you're not going to use this anymore, so I'm going to load that from memory, so it's already there by the time your processor gets to it. Like when that works, and it works a lot, it's like boom, you you have essentially kind of like infinite cache, right? Like it never, if you never have a cache stall, then your cache size is essentially infinite and it's like super predictable. So you don't need a big cache, but having a bigger cache means that you can have, you can have less predictable things or just bigger data sets, and it fits and loads in just in time, right? You have more chances to do that. Yeah, so how big is the code book in Block? There's like a lot less details in here than the other. Yeah, I think I'm gonna have to sign off sometime soon. My CPU is at like 7% right now. So my battery will be draining sometime soon. And it is 1:30. This is kind of interesting. So instead of 256, it uses 16, and that's faster. Well, it's faster on Intel CPUs, where 16 is just how it can vectorize, but on the vector engine with 255 or 256, it's kind of, it might be better. So yeah, I'm gonna look into this. I had a feeling, like I don't know where my notebooks are, but I've been trying to come up with an algorithm to leverage more memory than compute, because the vector engine, while it does have a good amount of compute, it's just like less than a GPU, right? These things are kind of really focused on the CPU and getting the CPU to its compute powers in this kind of scheme of load a bunch of matrices and multiply them together is, it's anemic compared to what the vector engine has. But then the vector engine is also kind of anemic compared to what a GPU has. So in order to level the playing field there, I'm interested in seeing how can we leverage the bandwidth advantage plus the fact that it can do more complicated things than GPUs to kind of make up for that. So I'm really interested in that. I'll probably look into this more later. Maybe in the next stream or something like that, I'll have something to start from, and we can maybe implement it on stream. That would be cool. I should probably talk to these people. I wonder if they're still in MIT. That would be kind of cool. But anyway, today was definitely a much more boring stream, as we didn't get the thing that we wanted to get working. But yeah, hope we learned something together, and happy to kind of interact with the chat. Thanks for participating, and I will be back next week with more shenanigans, and I'll see you guys there. So thanks everyone, and we'll talk later. Bye.